Hello and welcome back to Essentials of Computer Architecture and Organization. And in this lecture, we're going to be continuing our survey through the second major area that we focus on in this course, and that is on memory. We talked about caches and caching last time, and today we're going to talk about virtual memory technologies and virtual addressing. So this will be the last chapter that will be focusing on memory and virtualization. And so hopefully this will be starting to help you draw this all together. So first, what is virtual memory? It's a broad concept for a lot of variants. The general idea is you can hide the details in the underlying physical memory. This gives you a lot of flexibility in terms of implementation. It provides a view of memory that is more convenient to a programmer. And the goal is to allow the physical memory and addressing to be structured in a way that is optimal for hardware while providing an interface that is optimal for software. So how can you create something that's optimal for both hardware and software? You can with virtualization. A trivial example, let's talk about byte addressing. It's the architectures use byte addresses, and we talked about that previously. A byte could be like 8 bits. The underlying physical memory uses word addresses. The memory controller translates this automatically, so it's like a language translator, if you will, and we show this controller would actually fit in between. So this fits our definition of virtual memory. Virtual memory terminology, here's a couple of things for us to keep in mind. Memory management unit, MMU, it's a hardware unit and it provides translation between virtual and physical memory schemes. What about virtual address? It's generated by a processor, either instruction fetch or data fetch that translated into the corresponding physical address by the MMU. So a virtual address does not quote the real address, and then we have the physical address, which is used by the underlying hardware. This is where it actually exists. It may be completely hidden from the programmer. And a few other things, virtual address space. It's a set of all possible virtual addresses. It can be larger or smaller than the physical memory. Each processor may have its own virtual space. And finally, virtual memory system. This would be a system that contains all of the things that we just mentioned. So let's take a basic example. Multiple physical memories. Most computers have more than one physical memory module. You may have upgraded a computer before, and you put in physical memory, and sometimes there's several slots to put in those memory modules, and those are examples of physical memory modules. But what the computer sees, it's one contiguous set. Each physical memory module offers addresses 0 through n-1 for some n being the number of addressable areas. May use an arbitrary memory technology. We mentioned, for example, SRAM and DRAM. You might remember that from an earlier chapter. Virtual memory system can provide uniform address space for all the physical memories. So let's talk about a note about banks and modules. The concepts are similar, but let's point them out. For a bank, it generally refers to physical memory. It's used when identical memory modules are replicated. A module, on the other hand, is a more generic term often used with virtual memory systems. It's preferred when heterogeneous memory units are combined. So let's show an illustration of hardware for two dissimilar memory modules. So you have a processor, you have your memory management unit, and then you have your physical memory. You have the physical controller, and these could be different types of memory, maybe from a different manufacturer, maybe having different kind of characteristics. Well, how about virtual addressing for multiple modules? The typical scheme is a processor has a single virtual address space. The address space covers all memory modules. The memory management unit translates from the virtual space to the underlying physical memories. So for example, say we have two physical memories with 1 gigabyte each, and so we have a total of 2 gigabyte available. The virtual addresses are 0 through 3 FFFFF, corresponding to memory 1. The virtual address for and the whole of the rest corresponds to memory module 2. So if you know the underlying, how the relationship, you can see how the virtual address may have a unique mapping to the physical address. And we're seeing that in this example. Here's an illustration of the virtual addressing. So you have the memory 1, and just as we said before, here's the address space for that. And for memory 2, here's the address space for that. The processor sees it as one contiguous memory. It doesn't need to know whether it's using memory 1 or memory 2. And just as a reminder, 1 gigabyte, it gives, and here's the number for how many bytes that corresponds to. For identical modules, these are called memory banks. So let's talk about address translation. It's performed by the memory management unit. It's also called address mapping. For example, determine which physical memory test, if we want to test if the address is 4 and the rest of that, 40000 or above. Both memory modules use address 0 through 3 FFFFF. So we subtract the 40000 from address when forwarding request to memory 2. So that's how you go to the MMU, how it processes it and converts it to the address space in the physical memory. So here's an example in pseudocode of an algorithm to perform the address translation. You receive a virtual memory request from the processor. And here what we just talked about, if it falls into something that if it's greater than the 4000000, then you subtract that amount and then you pass it on to the physical memory. Otherwise, you pass the unmodified request. So how do we go about avoiding arithmetic calculations? Subtraction is relatively expensive. To optimize, we want to be thinking in binary. We can always divide the virtual memory space along boundaries that correspond to powers of 2. And so remember that this is, we can think of this in terms of shifting. Virtual addresses can be divided into 2 groups of bits that choose among underlying physical memories. And and then we specify an address to the physical memory. Note, selecting bits in hardware merely requires running wires, no gates and no computation. So here's an example in binary, and we're showing how the physical address works. And you can see what the relationship would be between those. The address above 3 FFFFF are the same as the previous set, except for the high order bit. So it's just this one bit. Hardware can use this high order bit to select a physical memory module. So that's going to be a lot easier than actually doing a computation, as we were seeing what was outlined in the pseudocode. Well, what about the address space continuity? First of all, the option of contiguous address space, all locations corresponds to physical memory. In this case, it's inflexible. It requires all memory sockets to be populated. On the other hand, you can have a discontinuous memory space. One or more blocks of address space do not correspond to physical memory. So in a sense, it has a hole. The fetch or store to any address in a hole causes an error. This is flexible. It allows the owner to decide how much memory to install. But you're going to have to be aware of that. And here's an illustration of a discontiguous address space. And so you have your memory modules, and you're thinking that you have this total amount of memory, but what you actually have is you have a couple of holes based on how much memory you populated into your computing platform. How about programming and discontinuities? We say we want to consider a program running in an address space that has holes. If the program attempts to store or fetch an address that corresponds to a hole, an error results. For most systems, holes are only relevant to operating systems programmers. For an embedded system, the application programmer may need to avoid holes. So what are the motivations for virtual memories? Let's talk about the hardware and the software perspective. From a hardware perspective, it allows multiple memory modules, provides homogeneous integration. From the software perspective, the programmer sees this as convenient as it offers support for multi-programming and protection. In terms of multiple virtual spaces and multi-programming, the operating system allows multiple application programs to run concurrently. One of the key things for an operating system to do for integration of information from one app to another. To prevent one application from interfering with another, each application runs a separate process. Each process has its own virtual address space that the operating system assigns it. The operating system arranges for the MMU to translate a given process address into the correct physical memory address. So here's an illustration of one way to map 4 virtual spaces. And so you have your physical memory, and so maybe one app has virtual space 1, another one for virtual space 2, a third for virtual space 4, and a fourth one for virtual space 4. And in reality, this is all cut right, it's right next to each other, but it wouldn't necessarily have to be in the virtual space. What about dynamic address space creation? Note that the MMU translates each virtual address to a physical address. The MMU configuration can be changed at any time, thus it can be dynamic. Typically, access to the MMU is restricted to the operating system. When the operating system runs, no mapping is performed. The processor only changes to virtual memory modes when running an application. Here are some example technologies used for address space creation. You can have a base-bound registers, you can have segmentations, or you can have demand paging. Let's talk about base-bound registers. It requires 2 special hardware registers, which is part of the MMU. The base register specifies the starting address, and the bound register specifies the size of the address space. The value is changed by the operating system. It's set before an application runs, so it gets information that how much memory does it need to operate. It's changed by the operating system when switching to another application. When that application is closed, it can free up that memory and that whole block that was used. It was once popular, but it's no longer used, but it might be conceptually easy for you to see what that would mean. And so we have the start and the finish of what this base and bound registers would mean. And so that's what we're seeing, and it goes all the way from 0 to M being how large this space has to be. Each processor's address space is mapped to a region of memory. What about protection using base-bound technology? It is a key for systems that run multiple applications concurrently. Each application is allocated separate areas of physical memory. The operating system sets base-bound registers before the application runs. The MMU hardware checks each memory reference. The reference to any address outside the valid region results in an error. We talked about that before. and it prevents an application from snoozing or changing another application's memory. Once that's said, but until it's released, it maintains that that ownership, if you will, of that memory. Well, let's talk about segmentation. It's an alternative to a base-bound approach. It provides fine granularity mapping. It divides a program into segments. Typical segments corresponds to one procedure. So how many of these little pieces of the physical memory puzzle, if you will, are you using? It maps each segment to physical memory. The key idea is a segment is only placed in physical memory when it's needed. When the segment is no longer needed, the OS moves it to disk. So it can give you the potential of more of your random access memory, your RAM, available. Well, what are the problems with segmentation? It needs hardware support to make moving segments efficient. The two choices are you can have a variable size segments, which can cause memory fragmentation, and you can use a fixed size segment, which may be too small or too large. So unfortunately, neither choice works well, and as a result, the segmentation is seldom used. What about demand paging? It's an alternative to segmentation and base-bound approaches. It's currently the most popular virtual memory technology. It divides a program into fixed size pieces called pages. No attempt is made to align pages boundaries with functions, objects, or large data structures. Typically, a page size is 4K bytes. Only some of the pages of a given application are in memory at any time. Others are kept on the disk and fetched when they're needed. So for demand paging, it allows a physical memory allocated to a process to change over time. Well, let's talk a little bit about demand paging support. The hardware is needed to handle address mapping and detect missing pages. So there's a role for the hardware, and then for the software is needed to move pages between the external store and the physical memory. So let's talk about the page hardware first. It's part of the MMU. It intercepts each memory reference. And if the reference page is present in memory, it translates the address and performs the operation. If the reference page is not present in memory, it generates a page fault, that is an error condition, and it records the details and allows the operating system to halt the fault. So it's like generating an exception, and there's a way to handle the exception. How about the demand paging, the software? Let's talk about that. So it is part of the operating system. It works closely with the hardware. It's responsible for the overall memory management, and it determines which page of each application to keep in memory, which ones to keep on the disk. The records location, it keeps a records location of all the pages. It fetches pages on demand when an application referenced an address that is not in the memory, and it configures the MMU. So that gives you a little bit of an idea of the parts done by the hardware and the part done by the software. Well, what about page replacement? When a computer starts, the application runs and references pages. Each reference page is placed into physical memory. And eventually, the memory is completely full. An existing page must be written to disk before memory can be used for a new page. So choosing a page to expel is known as page replacement. In terms of optimization, you can replace a page that will no longer be needed soon. And so having a criteria for figuring that out, how long has it been there before, since it's been used? And so that's kind of one way of how you can be thinking about memory utilization with this approach. In terms of paging terminology, we'll introduce 4 terms. First, page, it's a fixed size piece of program's address space. Frame, it's a slot in memory, exactly the size of one page. Resonant is a page that is currently in memory, and resonant set, it's pages from a given application that are present in memory. How about paging data structure? This is known as a page table. One page table per process is how it's set up, and it's created and managed by the operating system. It's used by the MMU when translating an address. So we can think of a page table as a one-dimensional array. It's indexed by the page number, and the entry stores a pointer to the location of the page in memory, or a bit that indicates the page is currently on the disk. So here's an illustration of a page table, and you can see the page table it's not always linear where things are in the physical memory, which makes sense because it's as needed. If something is no longer needed, it's going to be replaced. So there'd have to be a mapping, but they're not going to be the same order. So each page table entry points to a frame in a memory, or if it doesn't point to anything, and you see a couple examples here, it doesn't point to anything at that moment. How about address translation with a page table? Given a virtual address V, we want to find the underlying memory address P. There's three conceptual steps. The first is to determine the number of the page on which the address V lies. Second, we use the page number as an index into the process's page table to find the starting address of a frame in memory that contains a specified byte. Third, and finally, it determines how far into the page address V lies and converts it to a position in the frame in memory. So how about we briefly look at the mathematical view of address translation. A page number is computed by dividing the virtual memory address by the number of bytes per page. And so that's what we're seeing here. And the offset within the page O can be computed as a remainder. And using the feature mod, we can come up with V mod K would give us the remainder. So we use N and O to translate the virtual memory address V to a real memory address. And so this is how we come up with that. So within the page table, we go to N, and then there's an offset O, and then we have the real memory address. Once again, using the power of 2 can be a real helpful thing for us to leverage. We cannot afford division or remainder operations for each memory reference. We want to be thinking binary and use powers of 2 to eliminate arithmetic. Each number of bytes per page is 2 to the K, and the offset O is given by low order K bits. Page number is given by remaining the higher order bits. So computation is shown here below. So why don't we consider an illustration of translation with the MMU hardware. And here the typical paging system uses 12 bits of offset, 4 kilobytes per page. And so we have the virtual address, and we talked about the N and the O ports of that. So the N points us to where we want to go in the page table, and that gives us a physical memory address for the base, and then we have an offset, and that's the last couple bits. And so that's how we can get the specific address. So what about the present, use, and modified bits? It's found in most paging hardware, one set for each page table entry, and it's shared by hardware and software. And so here we show what the purpose of the bits are. We have the present bit, the use bit, and the modified bit. And the present bit it's tested by hardware to determine whether a page is currently present in memory. The use bit is set by the hardware whenever the page is referenced, and the modified bit it's set by the hardware when the page is changed. So just some other practical things that are helpful. And let's talk about the page table storage. In some systems, the MMU holds page tables. Most systems place the page tables in memory. The interesting idea is the page table entry only is needed to store the address of a frame. Each frame is a power of 2 bytes, so the starting address will have 0 in the k lower order bits. Instead of storing zeros, it stores the presence, use, and modified bits. Thus, it allows page table entries to remain aligned at the word boundaries. So where are the page tables in memory? The typical position is above the operating system. And so this gives you a mapping of the memory, and you have the operating system, the page tables would come next, and then you have the frame storage. Consequently, only a part of memory is divided into frames that holds applications. So you have memory partitions and utilization in certain areas for different things. So let's talk about the importance of efficiency. When paging is used, an address translation must occur for each instruction fetch and for each data reference. So the translation can become a bottleneck and it must be optimized. Note, early virtual memory systems did not have special hardware for address translations and were unusable. Let's talk about the translation look-aside buffer, TLB. It's a hardware mechanism used to optimize address translation. It employs a form of content addressable memory, and we talked about that several chapters ago. And the hardware unit stores pairs of the virtual memory and the physical memory. If a pair is in the TLB, the virtual address can be translated without a page table reference. The MMU returns a translation much faster than a page table lookup. So in practice, a virtual memory system without a TLB is unacceptable. The TLB approach works well because application programs tend to reference a given page many times. It's principally known as a locality of reference. So in terms of the consequences for programmers can optimize program performance by accommodating the page systems. Examples are group-related data items on the same page and reference arrays in the order that accesses contiguous memory locations. So let's look at an array reference. Consider an array stored in a row major order. And so we have all of these rows, 0 to n, and the location of A, ji is given by the location A plus I times q plus j, where q is a number of bytes per row. Thus, accessing items by row makes repeated access to the same page before moving on. In terms of programming to optimize the array access, here is an optimal way of doing it, and here is a non-optimal way of doing it. And there's just some slight differences between how things are programmed between these two. And I'll just let you guys look over that, and you can comment on what you see as the difference. Virtual memory caching. You can build a system that caches the physical memory address and contents, and the virtual memory address and contents. And note that if the MMU is off chip, the L1 cache must use virtual addresses. The key point is multiple processors have separate address spaces, but each use the same set of virtual addresses. How about handling overlapping virtual addresses? Each application process uses virtual addresses 0 through n. The system must ensure that an application does not receive data from another application's memory. There are two possible approaches. The operating system performs cache flush operations when changing application, or the cache includes ambiguity tag with each entry that is a process ID. Here's an illustration of an ID register. It assigns each running application a unique ID that is a process ID. And the operating system places the ID in a special hardware register when the application runs. The memory system attaches the ID to each address in the cache. So all of that is associated with a process ID. So we've quickly covered a lot of material talking about virtual memory. Virtual memory systems present illusions to processors and programs that actually help. The underlying physical implementation is not necessary to see for some of these things, and they work quite well when you have that separation. Many virtual memory architectures are possible. Examples include hiding the details of word addressing, creating uniform address space that spans multiple memories, and incorporating heterogeneous memory technologies into a single address space. All of this is possible when we're using virtualization. Virtual memory offers convenience for programmers. It offers support for multi-programming, so you can have more than one program functioning at the same time, and you can have protection. 3 technologies have been used for virtual memory: base bound registers, segmentation, and demand paging. And as we highlighted, that the demand paging is currently the most popular. For demand paging, it's the chief technology used in most systems. It's a combination of hardware and software. It uses page tables to map virtual addresses to a physical address, and a high-speed lookup mechanism known as a TLB to make demand paging practical. Caching virtual addresses requires either flushing the cache during content switching or using an ID to disambiguate. So a lot of information there. Hopefully talking about memory is now a little bit clearer, and that'll be the last for this section. Thank you very much.